This series requires no special pre-knowledge on your part and is intended for everyone. With that said, let's get started. So, speaking of digital currency, how could such a thing exist? How could I send you some bits over the internet that would somehow be interpreted as money? Well, let's think of something we're all familiar with. Email. So how about this? Could this email, which states that it represents one e-money, be used to buy things that cost one e-money? Technically, it could. If enough people started passing these around and accepting them for goods and services, this would be a primitive sort of digital currency. It wouldn't be a very good one, however, in that I could do this. If I had sent you this e-money for, say, a subscription to your weekly blog, thanks for that, I could also send that very same email to my friend Sam, to my cousin Bob, and to my neighbor Mary. Now, all of a sudden, where we started out with just one e-money, we now have 4. Poof! New e-monies were simply created out of thin air. And I could technically do this as many times as I wanted. You can see how this is problematic because it means that our money supply can be rapidly expanded in a completely unaccountable way. If I can create as many new money units as I want, this currency would be what's called infinitely inflatable. Why wouldn't we want unlimited, unpredictable inflation? Let's consider gold for a moment. You know, that really valuable metal shiny rock. What would happen if, say, an asteroid were to hit the Earth that was made of gold and suddenly increased the available supply of gold by 1 trillion? So that there were gold coins lying around everywhere you looked. You wouldn't even be able to step out your front door without kicking over a pile of gold. If gold were as common as pebbles, do you think people would still be willing to trade, say, a car for an ounce of the stuff? I don't think so. In the same way that gold would be devalued if its supply were increased by 1 trillion, same goes for money. Kind of like this. As the supply of money increases, the purchasing power, or what goods and services each individual unit of that money will get you, goes down. As an example, in the United States there used to be something called penny candy. That was because 1 penny would buy you a piece of candy. Now, a lot of people simply throw their pennies away in the trash can because it will no longer buy them anything. If any new monetary system is to be considered worthy of your attention, it's got to not be like that. So, going back to our email example, how could we ensure that anything digital is not infinitely inflatable? Is the digital realm, after all, not the land of copy and paste? Yeah, like that. To prevent the copy and paste problem, inflation, from taking place on our special email money, e-money, what if we tracked every email that was sent on a kind of ledger? Like this. And what if we built a kind of wallet software that read this ledger? So if I tried to send you 2.5 e-monies, my wallet would know that I only have 1. This concept of a digital ledger makes up the entire foundation of digital currency, or as some also call it, cryptocurrency. And that foundation has a name: a blockchain. And now you can be confident that anytime someone drops this fancy word around you, all they're really saying is digital ledger. But if it's a digital ledger, why call it a blockchain? What does that mean? Well, it has to do with how this ledger works. Going back to this concept of a ledger, the most important thing we have to make sure of, to make sure that our monetary supply is open, honest, accountable, auditable, we have to make sure that the numbers are trustworthy. How can we make sure, for example, that I don't do something like this? Wouldn't that be convenient for me? Or how do we make sure that I don't do something like this? Alice never should have crossed me. Well, the answer is that no one gets to change the ledger. They only get to update it. Let's shrink this down. Here's that shrunk down copy of our ledger, and it's time-stamped. If we want to change who owns what, we have to add an update. And on, so that anytime I, you, Bob, Alice, or anyone using the e-money system wants to send some e-money, it gets included in an update. After a bit, you start to see where this digital ledger gets its name. Each update to the ledger is called a block, and the cumulative result of this is a chain, hence blockchain. Now you might be thinking to yourself, that seems like a novel way to try to do money, but who gets to make entries into the blockchain? When do they get to make entries into the blockchain? Any old time they want? And why should we trust that people making entries into the blockchain are making accurate entries? Well, my friend, that you would even wonder such a thing tells me that you are clever enough to have a complete understanding of all things blockchain and digital currencies, so why don't you hop on over to episode 2 to find out the answers to your questions. We ended with the questions, who gets to make updated entries into our e-money ledger? When do they get to make them? And why should anybody trust that the updates that they make are accurate? And all of those questions can really be summed up under one heading. Security. What is the security model of a blockchain? To understand that, we first need to conceptualize how a blockchain is run to begin with. And that is via a network, using the internet. The basis of the network is people keeping copies of the blockchain on their computers, and they are connected to one another via the internet. Irina in Russia communicates to Chen in China, communicates to Joe in Australia, communicates to Harry in Hawaii, communicates to Carrie in California, Marie in Mexico, Larry in London, and hundreds or thousands more people across the world, looking something like this. You get the general picture. And the purpose of this network is for all participants with a copy of the blockchain to agree on the state of that blockchain at any given time. For example, a situation like this in which Chen's copy of the blockchain reports that I have 3 e-monies, but Marie's copy reports that I have 47, would cause total chaos and would be of no use to anybody whatsoever. So the state in which all or the majority of the network agrees on the same versions of the blockchain is called consensus. And it is from consensus that a blockchain running network achieves most of its security. So, back to our example of Chen and Marie having conflicting copies of the blockchain. A big no-no, useless for everybody. How do we prevent that from happening and keep consensus about who owns what? I'm going to talk a little bit of computer science to you right now, but don't even worry, it's not a big deal. The mechanism used to maintain consensus on who owns what at any given time is called proof of work. And that just gives us a fancy way of deciding who gets to make an update to the ledger and when. See, the primary goal here is to not have both Chen and Marie broadcasting conflicting versions of our blockchain at the same time. We gotta have one or the other, so which is it gonna be? Chen's version or Marie's version? Using what's called proof of work mining, and I know it's weird that I would use the word mining, but you'll see why in a moment, we can maintain consensus. So back to a stripped down basic version of our network, right? What we don't want is two different people with copies of the ledger making an update at the same time. We want only one update to the ledger being made at a time, which everyone else can then take a moment to agree with and incorporate the update into their own copy of the blockchain. This is achieved using specialized computers called miners. Here's what one looks like. Yeah, they really are weird-looking, specialized computers. The computer code looking something like this, that makes our blockchain possible, contains a math problem to be solved. Seems kind of silly when I say it out loud, but I'm not kidding. The computer code has a self-adjusting math problem that these mining machines are built to solve. And the difficulty of the math problem is set to increase as the number of miners on our blockchain network increases. And all this fancy mumbo-jumbo is done to ensure one thing: that only one miner solves the math problem at a time, and that it happens consistently every few minutes. And what happens when a miner solves the math problem? Well, two things happen actually. First is that he gets a reward of newly created coins on the blockchain. Yes, I am not kidding. Newly created coins on the blockchain are paid to the miner who solved the math problem as a reward for proving his work. And secondly, he's the one who gets to create the next block. Or in other words, he's the one who gets to publish the next update to the ledger, containing all of the transactions that happened in the last few minutes. And thus does our blockchain, which is a chain of blocks, keep perfect record of every transaction that's made, the time that the block was published, and the total number of coins that exist, including the increase of coins, as the miners were paid in new coins as their reward. As an example, 1,000 coins, then 1,005, then 1,010, and on and on. In this way, our money supply, as recorded on the blockchain, can be considered open and honest. In other words, it's viewable to anybody. This also means that inflation, aka the new money created, is both transparent and predictable. What you need to know now is these accounts. They're not actually tied to your name. That wouldn't work at all. Accounts on a blockchain actually look something more like this. Long alphanumeric addresses, which are actually longer than these, are totally unique, and you can own as many of them as you like. What does this mean? What is this witchcraft? Well, it's based on a form of math called cryptography, actually, and you are totally smart enough to understand it. So hop on over to episode 3 to see how cryptography allows us all to have accounts on a blockchain. What we've discussed thus far is, in our hypothetical digital ledger of e-money, or, hey, our blockchain, the who gets to make updates to it are the miners. You know, those people with the funny, fancy math problem-solving computers. A miner gets to make an update to the ledger when their machine was the first one to have solved the math problem, this being done in a regular and orderly manner. And the reason why we are able to trust these entries into the ledger as being accurate is that the entire history of every unit of e-money is public in the blockchain. Just as an example, imagine that this is a zoomed-in snapshot of 2 consecutive blocks. If this block shows me having more units of e-money than I did in the last block, there has to be a transaction, a record of someone sending me that e-money for this block to be valid. If there isn't, not a valid block. Same would go for your balance. If this block shows you as having 0, and in the last block you had 2.5 units of e-money, again, there must somewhere within this block be a record of a transaction of you sending your 2.5 units of e-money somewhere else. If that didn't actually happen, invalid. And so then you may be wondering, how do people send units of e-money to one another to then be recorded in these blocks in the blockchain? And that takes us to what I told you today's lesson would be about. Cryptography is a form of mathematics that provides the basis for how different accounts on the blockchain interact with one another. And you don't need to understand cryptography, trust me, I don't, to understand how we use it. Remember how I mentioned in the last lesson that on a blockchain, our accounts aren't organized by something like our name, but are rather tracked by cryptographic alphanumeric addresses that look something like this. Psst, the word alphanumeric being a combination of alphabetic letters and numbers. There you go. So if you wanted to, say, pay me some units of e-money to pay me back for taking you out to lunch, I would send you this alphanumeric address, and that would be the address you would send the units of e-money to from your wallet. So our blockchain would show something like your address, unique from mine, having sent 3 units of e-money to my address. And the next block would be published to reflect this transaction. So that leaves us with the question, well, how did you make that transaction? Did you give a phone call to one of the miners and read them off your long alphanumeric address and read them off mine and say, hey, make the update? No. What you did was you broadcasted a message signed by your private key. Rewind. Your address, you know, the one where you receive payments and can then send on payments to others? There's another word for it. It can also be referred to as your public address. And guess what? The only way to move funds out of this address, that is the only way to spend from it, is to know the private key. And private keys are really long and look something like that. And they're stored right within your wallet, so it's not like you have to memorize them or something. And so that's how payments on the e-money ledger work. You receive funds to your public address, and you can only spend them. That is, you can only move them on the ledger if your wallet software contains the private key. That makes private keys super top secret because anybody who knows the private key for a public address can spend from it. That's why nobody goes around posting their private keys in online forums. It's just not done. So when using your hypothetical e-money wallet and you want to send Amanda 3 e-monies for covering lunch yesterday, all you as the user do is tell your wallet you want to send 3 e-money and click send. Easy enough. What your wallet is really doing, however, is creating a signature of your private key that only you know, that broadcasts the amount you want to send and to whom to the entire rest of the network so that they can update their ledgers accordingly. So that whole public address, private key thing, the stuff that's mostly managed by your wallet, that's the cryptography bit. See, I told you it wasn't that hard. And as a little bonus bit of knowledge for you, remember how mining is solving math problems? The math that those mining machines are doing are called hash functions, and they are based on cryptography. Cool, huh? So I have to say right now, congratulations to you, because thus far you already know everything you need to know about a blockchain. First, that it's a digital ledger. Second, that updates to it are mined. And third is that the account system, the sending and receiving bit, as well as the mining system, is all based on a form of math called cryptography. You win! You win the golden ticket for getting this far.